Hi class, this is going to be our discussion of scales of energy and scales of energy use. So a couple of you brought up these ideas of energy uses outside of science class. And so this is actually a good topic that crosses not only the different scientific disciplines, but also into economics, government, and into the ideas of environmental science as well. And so, why do we need to care about energy? Well, over the years, our amount of energy that we use per person has actually increased. And with that increase of energy per person, the world's population has also increased. So, if we multiply these two, we can see that it's only going to get more and more energy required, but we only have limited resources. So, what do? Well, this is a little bit of an outdated map that came from the EIA. And it shows over here on the left our energy inputs. So, where do we get our energy from? And it's a flow diagram to see where do we get the energy out, in what forms. And as you can see, this is kind of getting at the different types of energy sources that we're going to look at this semester. But 58% of the energy that was put in actually gets lost. And so we'll address this, but this is an excellent example of the second law of thermodynamics in action. And so we'll address that later on in the semester. So what is energy? Several of you have talked about this in your discussion board posts, but I really want to get this across. And again, this is another link to Feynman's lectures that I posted. And Richard Feynman describes energy as we really don't know what energy is. It's more of an abstract mathematical construct that we can calculate, but we really can't define it. So some of you defined it as the amount of energy is the ability to do work, but then if you define work is defined by energy. And so it's the cyclical process. So getting into the units, we are going to focus on the SI system, so the international system, and specifically it's the MIXA. So specifically focused on meters, kilograms, seconds, ampere units, and not centimeters, grams, or seconds, or English units. So if we look at the electromagnetic units, for charge, we're looking at coulombs, current, amperes, electrostatic potential. This is where volts come in, and resistance is ohms. If we're looking at thermal units, so remember temperature is a measure of average kinetic energy of a system, and that we are going to be measuring in kelvins based on the SI system. And so energy, power, pressure, and force are all derived units. And so let's look at that. So in each of these, this shows an example of the units of X, or of whatever is in brackets down here. And our basics are our meter, our kilograms, our length, which would be meters, our seconds, time, and coulombs would be our charge. All right, so for an example of force would equal mass times acceleration in this case. And we said that it was a derived unit because we can't measure force directly. We have to measure other things and do a calculation to be able to get at force. So Newton would be the unit that is derived when we multiply mass times acceleration. So Newtons have SI units of kilogram meter per second squared. And so we see the same thing for energy. That would be joules. And regardless of the type of energy we're talking about, if we're talking about energy, it's most likely going to be in joules. And so if we can get our units to kilograms, or mass times length squared over time squared, we are going to be in an energy unit. Power is another derived unit. This would be the energy per unit time. This unit would be the watt, which is equal to joule per second, which again would be your kilogram meter squared over second squared times per second. Okay. And then pressure is our final derived unit, and this would be force per unit area, and this, our SI unit, would be a Pascal. So this would be kilograms per meter per second squared. So there's lots of forms of energy, and it took a really long time to get at this idea of conservation of energy. That energy really isn't disappearing, but it's really just changing form. So going from kinetic to potential to chemical to thermal to what most people think of energy, but don't really know what it is Einstein's rest energy. And so this idea of conservation of energy, that a single number characterizing a system or a part of a system could be traced through time as it flows and changes, is actually one of the most important facts, or most important ideas in physics especially. And so with all of these units of energy, if we get back to this idea, like I said before, mass times length squared over time squared, regardless of the type of energy, we're going to be measuring energy. And so an example of that is if we looked at kinetic energy, we have the equation of 1/2 v squared. And if we look at the derived units for that, we get to mass over mass times length squared over time squared, or a joule, if it were kilograms, meters, seconds. If we're looking at work and potential energy, we have force times distance. Again, we have mass times length over time squared times length. So we get out that joule, or our energy units. If we look at work by pressure, so we're getting into gases and gas particles now, we have pressure times volume, which would be the force over area times volume. And again, we get mass times length squared over time squared. And if we look at thermal energy, so here sorry, my video's in the way. If we look at thermal energy, we get at this idea of 1/2 times the number of moles. So hopefully you're familiar with that. That's just kind of like a dozen, but in chemistry we're dealing with much smaller things than eggs, and so we have to have a much larger number. So that would be 6.022 times 10 to the 23rd, typically of molecules, since that's what we're talking about with thermal energy. The gas constant R, and then temperature in Kelvin. So over here, we can talk about the number of molecules. So the mole just takes it to a bigger, broader number. But regardless, when we're looking at this, it still takes us down to joules because of that gas constant, and it leaves us with mass times length squared over time squared. Electrical energy, again, is if we look at our units, we get to this would be electrostatic potential going to an electric field, going to force, and the force does work on a charge that is moved. So this would be our charge times electrostatic potential. And how are we measuring electrostatic potential in SI units? Well, what potential do you have to move 1 coulomb of charge through to get or lose 1 joule of energy? And so if we look at our dimensional analysis down here, 1 volt would equal to 1 joule over 1 coulomb, 1 joule per second over 1 coulomb per second, which would equal 1 amp or 1 watt per 1 ampere. We'll get more into electrical energy when we do our solar unit. And again, the quantum energy and Einstein's rest energy we will probably get into when we're doing our solar unit as well. And so quantum energy is the energy of light quantum. And this is looking at waves and wavelength, or frequency. We can convert it to wavelength as well. So we have Planck's constant. It has certain units associated with it, of joule seconds, and we have frequency. And so we know the energy of light, and we know frequency is 1 over time. And so we can solve for Planck's constant, which would be joule seconds. And the equation everybody knows, E equals mc squared, is actually Einstein's rest energy that showed that the mass itself is a form of energy with the speed of light as the conversion factor. So energy is, I'm going to move me again. Sorry, guys. So there is, energy can be described in all sorts of units. And it really depends upon the scale. So this is an example of the units of energy and power. And they're pretty much broken down in terms of the scale of the energy that we're talking about. And so if we look at global units here, this is getting to our world total energy consumption in exajoules, all of the stuff that we talk about on a grand scale would be our global units. Our industrial strength units would be the next size down. And these, you notice, are somewhere around 10 to the 9th joules. And this is our SI equivalent. And so we'll specifically look at that because that's actually, when we calculate it, close to 1 human year of work. And then we go down to our human-sized and child-sized units. So this is kind of on our scale. And so these would be our calories, our British thermal units, and our kilocalories. And then finally, we get down to our micro world units of electron volts, and ergs. And so this gets down to the amount of energy of electrons. And so we'll be down in this land for a lot of our solar and photosynthesis, and some within our cellular respiration as well. All right, so if we look at our power units, again, this would be our watt, our foot-pound per second, and our horsepower. But when we think about converting between power and energy, these are the units that we're going to be talking about. So 1 megajoule is approximately 5 to 10 hard-working humans working for an hour. And so if we look at this idea of the human year, it's looking at how much energy, how much 100 watts is an average value for power production by human labor. So 100 watts for 8 hours a day for 200 days a year, because, there's got to be vacation. The human year then becomes 580 megajoules. If we look and convert that to other things to see how that compares, we can see really the scale of the amount of energy one human could work for a year. So a solar energy output in the year is 2.1 times 10 to the 26th human years per year. The annual human energy consumption in 2005 was 490 exajoules. So this was times 10 to the 9th. So the efforts of it, more than 100 times the Earth's population for a year, was the amount of energy that we consumed in 2005. Some other ideas. So I will post these slides so you have these conversions, because I think it's really cool to show your students. So the annual output of typical nuclear power plant, efforts of 2 times California's population for a year, the energy consumption Actually, this one's really cool.